Hello, everybody. Thank you for joining us for another edition of our webinar Wednesdays. Today, we're excited to have a great presenter here giving a presentation today on the analysis of dioxins and furans. Today, our speaker is Nicole Brown. Nicole is currently the Senior Project Manager at the ALS High Resolution Dioxins Laboratory here in Houston, Texas. She has 10 years of experience with the High Resolution Laboratory. She graduated from the University of Houston with her Bachelor in Science degree in Biology in 2007. Currently lives in Katy, Texas, just here a suburb of Houston. She enjoys running as a hobby, whether it be in downtown Houston with the running club or just in her neighborhood. So Nicole, thank you for taking time today to give the webinar Wednesday today, and I will turn it over to you.
Good morning. Thank you all for joining me today for a presentation about dioxin furans compounds. Today I will be talking about polychlorinated dibenzo P-dioxins and polychlorinated dibenzo P-furans, commonly referred to simply as dioxins. I will begin with a basic overview. I'll talk about what are dioxins, where do they come from, how are they toxic, what are some of the regulations with low detection limit requirements, and how high-resolution GCMS technology utilized by the ALS Houston Dioxins Laboratory meets these needs. Then I will go over example excerpts of data to provide a better understanding of how to interpret the results. So what are dioxins? Dioxins furans are a class of polychlorinated coplanar isomers with a unique chemical structure, differing by the number of chlorine substitutions on the molecule. The basic structure is the same, the difference being the number of chlorine substitutions. There are 17 monitored dioxins and furans compounds, which are considered to be the most toxic due to their stable coplanar structure with a 2,3,7,8 substitution of chlorine atoms. It is the substitution of chlorine atoms on the molecule in the 2,3,7,8 positions that renders the toxic, disruptive interaction with the genetic AH receptor, a transcription factor involved in the expression of multiple functional genes responsible for the production of enzymes and proteins. The most toxic is 2,3,7,8 TCDD, tetrachlorinated dibenzo P-dioxin. You might remember TCDD is the chief offender in Agent Orange. These compounds are carcinogenic, cause immune system, reproductive, and developmental problems, in addition to other damaging effects. As a matter of fact, they are classified as a group 1 carcinogen, which is the worst kind. Pictured here in the slide is 2,3,7,8 TCDD, and you can see the chlorine substitution here in the 2,3,7,8 positions on the molecule. Dioxin furan compounds are persistent organic pollutants. They do not break down very easily in the environment due to their stable, non-volatile nature. The half-life in surface soil is estimated to fall between 9 and 15 years, and in subsurface soil anywhere between 25 to 100 years. They are hydrophobic, repelling water, so they tend to adhere to the particulates or residual sediment in water samples. They are extremely lipophilic or fat soluble and stored in the adipose tissue in animals for many years. Accumulation over time through chronic exposure is called bioaccumulation. Dioxins also accumulate in the food chain. The half-life in the body is estimated to be somewhere between 7 and 11 years. So where did they come from? Natural sources of dioxins are forest fires or volcanic eruptions. However, the largest source of dioxin contamination comes from industry-related processes. Examples include the production of PCBs, pesticides such as Silvex, or herbicides such as PCP. Another source is the bleaching of paper pulp from paper mills producing dioxin. Uncontrolled waste incinerators, including solid waste and hospital waste, and even backyard burning, are all major contributors in dioxins furans production. Motor fuel combustion is another source. Both diesel, and gasoline. The deposition of dioxins furans into the environment from all these varying sources causes entry into the food chain, and that is where 90% of human exposure comes from. Part of the reason dioxins are so challenging to the expert toxicologist is the fact that the dose associated with a statistically significant increase in adverse health effects is extremely small. This has led to a wide range of efforts to clean up environmental contamination of dioxins, monitor wastewater from chemical plants, and regulate food such as fish, meat, and dairy with regular inspection requiring testing. Here are the 17 monitored PCDD, PCDF compounds and their respective method reporting limits in water and soil matrices. As you can see, they have very low reporting limits in the ppq range for water, reported in picograms per liter, and the ppt range for soil or sediment, reported in nanograms per kilogram. And many regulations have requirements which are even lower than these reporting limits. So, to reach these ultra-low limits, you need very sensitive instrumentation. And that, my friends, is what high-resolution GC, high-resolution MS technology provides. ALS Houston goes a step further by using an extra lowest calibration point, half that prescribed by the method, providing even lower reporting limits. So how small is a ppq or ppt? ppq, parts per quadrillion. The example below puts this into perspective to help understand this magnitude. Lake Tahoe holds 40 trillion gallons of water. That is 151 trillion liters. The lake is 22 miles long, 12 miles wide, and 1,600 feet deep. A single can of 12-ounce soda poured into Lake Tahoe is 1 ppq. Now for PPT, parts per trillion, a good example I have seen is 1 drop of water in 20 Olympic-sized swimming pools. Each Olympic pool holds 660,000 gallons of water, or 2,500,000 liters. So you can imagine that's a huge magnitude there. So on the next slide, we're going to look at some of the regulations requiring low detection levels. These are common examples of maximum allowable levels. So for the U.S. Safe Drinking Water Act, the maximum allowable level is 30 picograms per liter for the one compound 2378 TCDD. The Superfund sites for soil and sediment have a maximum allowable level of 10 picograms per liter for the TEQ calculation, which we will go over in a few minutes. The Whole Foods requirement for fish, in order to sell fish at Whole Foods, you have the combined TEQs for dioxins, furans, and dioxin-like, or the WHO12 PCBs, is 2.16 ppt, or picograms per gram. So it's really low for fish. The European Union concentration limit in waste is 15 ppb, and their European Union concentration limit in foods is 10 to 15 ppq. MPDES wastewater permits require a level of 10 picograms per liter for 2378 TCDD and below 30 picograms per liter for 2378 TCDF. Okay, so the dioxin furan analyses are performed utilizing high-resolution gas chromatograph with a high-resolution mass spec, the gold standard for dioxins and PCB congeners analyses. This type of instrumentation is required. It is required for EPA methods 1613B and 8290. The gas chromatograph provides compound separation. The retention times of the native compounds are based on the known retention times of the corresponding carbon-13 isotopically labeled standards, which helps ensure accurate identification of the dioxin and furan compounds. And the high-resolution mass spec as the detector provides the required capability of performing selected ion monitoring at a resolving power of at least 10,000 in order to distinguish between the masses. The HRMS used as the detector provides superior sensitivity, high mass accuracy, and precision. The very precise mass values result in the necessary high resolving power. With this technology, we're able to meet the detection and reporting limits required for these analyses. As illustrated in the example below, the detection limit for 2378 TCDD in a water sample can be as low as 0.5 picograms per liter. Now, as I mentioned earlier, ALS Houston goes a step further by using an extra lowest calibration point, half that prescribed by the method, providing even lower reporting limits. And you can see this calculation here for resolving power is simply the mass of one of the ions divided by the difference between the two most abundant ion masses there. And that's how you can tell what resolving power is required. So for dioxins, it's 10,000. I think for PCBs, it's 8,000. Now I'll talk about common questions regarding the data. Here's an excerpt from a report for a method blank associated with a PE sample. Next to the analyte name, we have our results column. ND indicates a non-detected result. I have zoomed in on the data here. Next to the results for 1, 2, 3, 4, 6, 7, 8 hepta-CDD and OCDD, you have the qualifiers J and K. The J qualifier indicates the result is an estimated value, since the concentration is detected above the detection limit. However, it is below the method reporting limit. The K qualifier indicates the ion abundance ratios between the primary and secondary ions were outside the expected range. The reported result is a calculated result that is the estimated maximum concentration, called EMPC. The calculation for EMPC can be found in method 8290. This is the most conservative result. Please note that EMPCs are not reported for regulatory or compliance samples, since having the ion abundances outside the expected range would mean all the peak identification criteria were not met for that result, and therefore would not be reportable in order to meet compliance rules. You also find an abundance of EMPC values at the very, very low levels. Now let's examine EDL. That is the estimated detection limit. Most users want their data reported down to the EDL, with many regulating authorities having action limits in the J qualified range. The EDL, as prescribed by the EPA methods, is the actual detection limit determined at the time of analysis. The EDL is affected by instrument sensitivity and sample matrix effects, as opposed to MDL, which is a statistical number. And of course, the MRL is the method reporting limit. In this next example, we examine the total homolog groups, and that is and why that number often differs from the sum of the specific results in each group reported. For example, sometimes we have clients asking why the total hexadioxins, total homolog group for hexadioxins are not equal to the sum of the 3 specific hexa-CDDs reported. Well, part of the answer is that the total homologs includes both specific compounds, those included in the list of 17 compounds reported, and non-specific compounds, which are not individually reported. In addition, if a value is reported and is qualified as EMPC or qualified with a K flag, that result will not be included in the total for that homolog group. Okay, so now we'll go over the isotopically labeled standards. Dioxins furans are also unique in that there are labeled compounds used for the analysis. Each specific dioxin furan compound has a corresponding carbon-13 labeled standard for identification. The identification of dioxins furans compounds is based on their elution at the exact same retention time as the labeled standards and the quantification of the 2 most abundant ions. For compounds without a labeled standard, for example, OCDF and one of the hexa-CDDs don't have a labeled standard, they are identified when their relative retention times fall within the respective windows as demonstrated in the ICAL and the quantitation of the 2 most abundant ions again. Here in the example, you can see the percent recoveries for the carbon-13 labeled standards here. So those are supposed to fall in between these control limits. But even if they fall a little below or above those limits, Sometimes they do, because of the precise nature of having the isotopically labeled standards, we still can quantify very accurate results despite those standards being outside of the range. Okay, so next, finally, I will go over the TEQ calculation. I get a lot of questions about TEQ. This is a toxicity equivalence calculation that reflects the total toxicity in terms of 2378 TCDD for a sample. Each of the 17 compounds are assigned a specific TEF, which stands for toxicity equivalent factor, which is a ratio of the toxicity of one of the compounds compared to the toxicity of the most toxic compound, which is 2378 TCDD. Here we have the three most commonly used sets of TEF factors. The EPA and World Health Organization define these factors, and they have been revised several times throughout the years. Here we see the TEF factors from 1989, 1998, and 2005. Okay, now this is an example calculation as it would be reflected in your report. So in order to calculate the TEQ, you take the result of each individual compound and multiply the respective TEF factor. For example, the result here for 2378 TCDF is 209 nanograms per kilogram. The respective TEF factor is 0.1. So you multiply 209 by 0.1, and that gives you 20.9 nanograms per kilogram. And then that's your adjusted concentrations in this column. Once all the results have been adjusted based on the TEF factors, you sum them all together, and this is the TEQ value. Another consideration for TEQ calculation is how to calculate the non-detected compounds. Some projects require using 1/2 the detection limits as the sample result for non-detected compounds. Others use an even more conservative approach by using the full EDL value as the result for non-detects in this calculation. Also important to note, for clients also testing for PCB congeners by method 1668, that there is a separate TEQ using the WHO-12 list of PCBs calculated in the same way for those compounds. So, and here's some pictures of our Houston high-res lab. Remember, ALS can test a variety of matrices, including air, tissue, soil, water, food, and many other products for dioxins. We have over 15 years experience, extensive experience in applying HRMS methods for dioxins, furans, and PCBs, and we hope you will contact us for more information. This concludes my webinar today, and I'm open for questions.
Thanks, Nicole, and thank you so much. On the questions, if there's several different ways you can ask a question. You can either click the little hand to raise your hand, or you can just type something in the chat box, or you can submit a question through the question panel. So I'll keep an eye on that, and while we're waiting for maybe some questions to come in, I do just want to throw a couple reminders out. One is that while we do have this high-resolution laboratory in Houston, Texas, in the United States, I know there are several folks from Canada on this webinar. Our laboratory in Burlington, Ontario, has high-resolution capabilities as well, and can analyze for dioxins and PCBs, PCB congeners, and those things as well. So that laboratory in Burlington, Ontario, can do a lot of this as well. Another thing I want to mention is just for Webinar Wednesdays, if you go to alsglobal.com and search Webinar Wednesday, you can see a list of upcoming topics that we have scheduled. And then I also want to mention that we are recording the webinar today, and we will post this on our YouTube channel, and we will email all of the attendees a link to that as well. Nicole, I do have a question coming in from Catherine. She says, could you repeat the bit about the calculation of the total? I think you said the K flagged values are not included in the total.
That is correct. For the total homolog groups, the EMPC values are not included in total homologs, but that they are included for TEQ calculation.
Okay. Thanks. And then we have a question from, and Catherine, if that didn't answer your question, let us know. We have a question from Lori. If standards recovery falls outside recommended ranges, how do you know your results are still accurate? Would there not be a considerable plus minus margin around the results?
Though that data would have a Y qualifier indicating that the labeled standards fall outside the expected range, and sometimes one or two are outliers and fall outside of the quality range. But because of the isotopically labeled standards and the precise nature of our testing, because not only you have three things going on when they identify using high res. You have your two most abundant ions quantified by the mass, plus you have your retention times. And because of the precise nature of the high res testing, even when the label standards are down to 10%, we can positively identify the compounds. It's really amazing, the technology that we have. But according to our method SOP that we have here, we do report data as long as those labeled standards are 20% or above.
Thanks, Nicole. We had a question about PCBs. This presentation is not covering PCBs, but if that's something that there is interest in, we can certainly add that to our list of future webinar Wednesday topics, because we can certainly do an extensive presentation about PCBs and PCB congeners as well. We have Catherine had a follow-up question. Could you please elaborate on why data is considered very accurate when the labeled standard fails? NFG guidance requires flagging when labeled standards fail, and we end up with a lot of J-flagged data.
Well, the J flags typically are only used for our analysis when it's an estimated value when the result falls between the EDL, that's the estimated detection limit, and the method reporting limit, and that's where you see your J flag data, and that's not really that doesn't really have anything to do with the Y flag, which is the labeled standards. When the labeled standards, that's the spike that we put into the sample, come back a little low, it means you lost some. So we usually re-extract, and we try to have our label standards within the required limits. But if it's not possible to re-extract, we do report those values qualified with low labeled standards. But as long as all the other identification criteria are met and you have good detection limits, we see that data is very accurate, and that's just based on experience. I can get you more technical answer from our technical director if you need me to.
Okay, yeah. So, okay. Catherine, if you have anything further on that, email Nicole, and she'll be happy to work with you on that. We have a question. Sure. We have a question from Julie. Should EMPCs be treated as detects or non-detects?
It depends on who's looking at the data. For regulatory compliance samples, such as wastewater for NPDES, you would treat that as a non-detect. Method 1613 does not include EMPCs mentioned in that method, but method 8290 does. The EMPC calculation is used for 8290. So you actually are required to use EMPC if you're running by method 8290. But for 1613, if you do not want to see EMPCs reported, you do not have to. As a standard practice, our lab reports EMPCs just to be on the most conservative data reporting. But for wastewater samples for permits, you won't see EMPC values. They will be reported as non-detect because basically the two most abundant ions are not falling within the range you expect them to fall in. So they're expecting a certain percentage of those two most abundant ions, and when they fall outside of that range, then you're questioning that positive identification of the quantity. So, I mean, even though you've positively identified the compound, you aren't as sure about the quantity because you may have some interference there with the same ion interfering. So that's why you would want to flag that data and report it as the MPC.
Great. We have a question from Toby. What is the quickest turnaround time for a soil or sludge sample and the corresponding cost above normal turnaround time?
Yes, for a soil or sludge sample, normally the fastest turnaround time is 4 to 5 business days, and we charge a 50% surcharge for that rush turnaround time analysis.
And just to expand,
the price really depends on how many samples are in your project and whatnot, and some of your reporting requirements and that sort of thing. But a basic price for one sample would be around $425.
Nicole, can you just expand on that and talk a little bit about the standard turnaround times? Because he asked about rush, but I'm sure some people are curious about standard turnaround times.
Yes, our standard turnaround time is 15 business days for dioxins and furans and 20 business days for PCB congeners. Of course, we can make exceptions when we have regular projects. Sometimes projects require a little bit smaller turnaround times of 10 to 15 business days, and we'll work with you on your turnaround times and try to meet your project needs and price it appropriately.
Great, thanks, Nicole.
You're welcome.
If it doesn't look like there are any other questions right now, so thank you so much, everybody, for attending. And Nicole, thank you for taking time today for Get Together presentation. I thought it was very informative, especially on the reporting side of things. And I just want to reiterate that we do have, for the Canada folks, we do have the Dioxins Laboratory in Burlington, Ontario, and I think I'm sure they will be doing a presentation in the coming weeks or months as well about some of their capabilities. If you have any questions, feel free to reach out to Nicole or myself. Nicole's email address is nicole.brown, nicole.brown@alsglobal.com. My email address is jared, Jarrod, .evans, EVANS, @alsglobal.com. If you have any questions about Webinar Wednesday topics, feel free to reach out to me. If you have any questions about our dioxins analysis, feel free to reach out to Nicole. Thank you all so much, and keep an eye out for future Webinar Wednesday topics. Have a good day.
Yes, thank you.